Hi everyone, I'm very honored to be here and have an opportunity to share with all of you about my research on language models. I was very excited to be visiting Ithaca for the first time and asked ChatGPT, where should I visit in Ithaca? ChatGPT gave a response that was very impressive. It's perfectly fluent, perfectly coherent, and all this information is factually correct. And they seem like great recommendations. I've already been the first and the third one, and I'll check out the second one tomorrow. So I'll see how to do. I was also very excited to meet Claire, my host, for the first time in person and ask for Claire's biography. ChatGPT gave a good response, but this time, at some point, it starts to generate factual errors that appear to be promising. For instance, it makes errors on her undergrad university, PhD advisor, and the graduation year, among others. At this point, we are probably all on the same page that these AI systems that deal with human language are hitting a historical milestone. They're making a direct impact on my life, your life, and the broader society. They're sometimes satisfying and sometimes not. So what are these systems? We need to understand a language model. It's also often called a large language model or a foundation model, but in this talk, I'll call it a language model. It is a machine learning model that maps an input X to an output Y. Here, X is a prefix of a sentence, and Y is the word that comes next, or X is a sentence with a blank, and Y is the word for the blank. These are two different types of models that I will use interchangeably throughout the talk. An important aspect here is that this supervision can come from raw text data with no explicit human labeling. So a typical pipeline is we collect massive text data, crawl on various web sources like Wikipedia, books, and news. So we have billions and trillions of words, and we learn tens of billions of parameters from this data. For every input, the model outputs a probability distribution, and we maximize the likelihood of the correct word. Once training is completed, the data is discarded, and these parameters can remember many things from its training data. For instance, it knows that the capital city of New York is Albany, Pike Place Market is located in Seattle, and hello in Hawaiian is aloha. I simplified a lot, and there are many behind-the-scenes stories about how I came to understand how these models work and how I could improve them for downstream uses. Part of my research was about this, and we'll go through some of them throughout the talk. Nonetheless, today's language models do have many problems, because fundamentally, this finite set of parameters cannot remember everything about the training data. It fails to remember many pieces of information like Claire's PhD advisor. In fact, I was surprised when we discovered that even commercial state-of-the-art models like ChatGPT make errors for 42% of the cases. Some believe scaling can solve the problem. However, aside from the fact that this is only possible to a handful of tech giants, which is undesirable, they were unable to solve the problem even after spending hundreds of millions of dollars. This indicates it's not just about the resources you have. Not only that, it is often just impossible to be correct because the word changes dynamically, and there is no way the model knows events happen after its training. For instance, I asked ChatGPT the relationship between Google and DeepMind. Then ChatGPT says these are separate companies, even though they were words, because these words happen after ChatGPT's training. Finally, I should mention that current language modeling practices completely ignore responsible data use. Training data of these models include lots of data sources that are copyrighted, non-permissive, or even private. And because there is no way we can credit back to data creators, this has been a big problem to the broader society, represented by many ongoing lawsuits, including the one by New York Times a couple of months ago. To address these problems, my PhD research asked, can we rethink data use in this language modeling pipeline? And what I mean is currently, we discard the data after training and solely rely on model parameters, hoping they remember everything about the data. What I think a model should do is instead of discarding the data, keep the data and use it together with parameters as inference. For every test input, the model should be able to locate relevant pieces and reason about them to make a prediction. We call this data a data store to distinguish it from the training data. And now, by definition, the model can better capture the full distribution of the data. Also remember, this data store is flexible and can change at any time. That means now the model can grow by extending the data store or be seamlessly updated by keeping the data store up to date. For instance, by adding breaking news to the data store. Finally, these models open up a new avenue for responsible data use by separating permissive and copyrighted data and using them differently. I'll talk about how exactly we can do this in a minute. So today's talk is structured as follows. I will start with discussing how we came to understand how current language models work before discussing any new models. I'll focus on one of the most surprising capabilities language models have, which is to learn a new task from labeled data at test time with no explicit training. This feature makes language models sound very mysterious because it appears to be learning a new task on the fly. However, my work showed that this is not true. Instead, the model works by activating patterns seen during training. Moreover, we show we can further train these models to better activate this pattern. Each of these had considerable impact on the community in that it opened up a new line of work in critical understanding of language models and impacted subsequent work in adaptation of these models. Next, I'll discuss non-parametric language models, a new class of models that uses a massive text corpus as a data store together with parameters at inference time. We call it non-parametric because the model complexity can grow and change with respect to the data store. This is unlike parametric models whose complexity is bounded a priori. My research has been some of the first represented work in two different approaches in non-parametric models. I'll tell you what technical challenges there are in training such models and how we came to address them. Our experiments show these models can better capture the long-tail distribution of the data like factual information and can be easily updated by replacing the data store. Finally, I will discuss how we can make these models more responsible. In particular, training on all web data, including copyrighted data, can be problematic. We propose to separate permissive and copyrighted data, learn parameters on permissive data only, and to use the rest of the data as a data store queried only at test time. This gives performance that is close to training on everything, while protecting rights for data creators and lowering risk for model developers. Throughout the talk, you will notice that rethinking is a central theme for this talk. We'll first discuss rethinking the way current models use the data. Then we'll talk about rethinking how future models should use the data. And finally, I'll discuss rethinking which data the model should use in what way. So let me get started from understanding current language models. Today's language models can perform a wide range of different tasks with no task-specific training. For instance, if you wanted a sentiment analysis, which classifies whether the text is positive or negative, you can do this by formatting an input in a way that a completion of it will naturally give you a prediction, and feed it to the model to get the prediction. You can do this for many different tasks like question answering and translation simply by changing the input to the model. Because again, a lot of tasks we care about can be casted into a sentence completion problem. So the model can do the task fairly well in this setting already. But what's even more amazing is, according to the GPT-3 paper in 2020, this model can learn from labeled data at test time with no explicit training. Suppose you have a labeled data set like this, and previously, if you want to learn from this data, you'll go through a training process with parameter updates. And only then you can use it for a new testing. In contrast, what GPT-3 does is to concatenate labeled examples into a single piece of text, put the test input to the same format, and feed into the model to get the prediction. Everything is inference only. There is no separate parameter updates. We call it in-context learning because it's like learning a new task, even though there is actually no training. Now, in-context learning was literally the most important breakthrough in NLP in the past few years. The idea of having a single model performing many different downstream tasks is already incredible. And the fact that we can do this by learning from labeled data at test time just sounds very magical. At the same time, this was very mysterious. We were not really able to understand how the model can possibly learn a new task at test time. In fact, I was curious, is it even true that the model is truly learning a new task on the fly? We sought to answer this question by asking an adversarial question. How far can you get without correctly labeled data? And what I mean is, instead of using correctly labeled dataset, how about we use a randomly labeled dataset? Now, this does not make sense anymore, because then there is no way the model can get the right supervision about the task. I did not expect this to work, and I'm sure the rest of the community did not expect this to work either. But it turns out it works as well as original in-context learning. These are the results of over 10 multiple choice datasets. X-axis is a range of language models, including the largest GPT-3. Y-axis is model accuracy. This is a random guessing performance as a reference. This is no in-context learning without label data, also as a reference. This is in-context learning with correct labels, so standard in-context learning. And this is in-context learning with random labels. Its performance is very close to original in-context learning. In fact, it recovers over 95% of the original accuracy. So we try to understand what is happening. And to be clear, using label data is still better than not using label data. The label data is clearly doing something. Our conclusion is that the label data does not teach the input-output correspondence, unlike previously thought. Instead, it teaches the task format, such as the domain of the text and the overall formatting of the string. Then the next question you may have is, then where does this input-output correspondence come from? We think it's likely coming from language models' training data. Training data of these models is massive and naturally reflect a range of tasks we care about, such as figuring out the sentiment of the text. So it's likely these models have captured this correspondence during training, and in-context learning is mainly about activating this correspondence. After we published the paper, people found this broadly hold for a range of brand new models across different tasks, data sets, and settings. Personally, the more exciting part was our work has led to a follow-up work that discovered other unexpected behavior of in-context learning and language models in general. Yes?
Could you explain the previous slide a bit more? So, you're saying that, for example, this slide, you're saying that the training data has all these reviews, but I'm not sure I understood where it learned that this review is positive and this review is negative.
Yeah, so the question is, with this unstructured text, how exactly does the model learn to say positive or negative? That's a great question. And all of these are hypotheses. But I think what it does is by predicting the next word, it learns how to say a positive word condition on positive sentence, or say negative word to negative sentence. Of course, that does not mean you have this structured format of saying positive to a positive review and negative to negative review. So that format is obtained at inference. Yes?
To make sure I understand your setup, you're saying that in the in-context setup, you're labeling randomly, but you're evaluating still on the true label.
Yeah, so we are only replacing labels for the the training data part, but the evaluation is still against the original gold label. Yeah, I can continue. Yeah. So we also did some fun collaborations. For instance, I met Boshi and Tuan at a conference where we discussed how this can be applied to reasoning. We specifically focus on chain of thought reasoning, which is one of the most popular methods to get reasoning abilities out of the language model. This is basically in context learning. So you use questions and answers, but instead of directly using the answer, you use a rationale that includes reasoning to get to the answer. Then the model can give you a solution and answer to the test answer. What we try is to twist this rationale in a way that its underlying reasoning is totally off. The model still gives you a correct solution in the answer. In fact, it recovers over 90% of the original accuracy. So far, I discussed understanding in context learning. But can we use these insights to improve model performance?
Can I ask you, rather, how or what is it that you're asking about? Like, instead of labeling positive and negative reviews, I could label reviews that are about action movies and versus reviews.
Yes, exactly. Yeah, exactly.
Documentaries.
Yes.
How does he know what the task is?
Right, exactly. And I think that's exactly the role of in-context learning. You give a label data to tell the model this is the task you are supposed to do. But the actual capability to do the task was already obtained during training. That's our hypothesis. Yeah, there's a question about it.
So that's the case. What's the key? Why does it not misinterpret task when you give it false labels?
Yeah, so the question is why does it not misinterpret a task? That's a really great question because there's actually a follow-up work after we published, which is what if the task defined by this label example is ambiguous? And I think they have an interesting analysis. Maybe I should send a reference paper to you offline. But yeah, they did study that, and then in that case, that could be more complicated. But unless the task defined by label data is unambiguous, then the model can do the task as expected.
What's the purpose of the mislabeled data? Like, if it's ignoring the labels and it somehow understands the task regardless of labels, then what's the purpose of it?
Oh, so what's the purpose of the mislabeled data?
Yeah, like, how does it indicate the task?
I see. So our hypothesis is that if the task align with the semantics that the model has learned during training, then the model can follow the task. So for instance, saying positive to a positive view, saying negative to a negative view is quite unambiguous, and it matches what the model has seen during training. When it does not exactly match, or when there can be multiple ways to match what have learned during training, then it can be complicated. So these results are on cases where the definition of task is more clear. Oh, yes, question?
So did you find examples of tasks where using random labels deteriorated performance?
That's a great question. So the question is about, is there other tasks where using random labels could hurt the performance? One thing we found is when it comes to generation, then using random labels could hurt. For instance, actually this is an example where if you're putting a exactly random answer to the question, then it would work very well. So in this case, you have to meet certain conditions. Like it has to be still relevant to the question. It should be using keyword from the question. But then the underlying reasoning can be wrong. So when it comes to generation, there could be more complicated conditions coming up. But the high-level idea that it does not have to be the exactly correct answer to the question still holds. Yeah, I can continue and get more questions at the end. Yeah, so the next question I want to ask is, can we use these insights to improve model performance and make sure the model can better activate the correspondence and do better on a new task not seen during training? And to remind you, the state at the moment was to take the language model as it is and do in context learning. But can we add an additional step here? So our proposal is to add a second stage training where the model is trained on a large, diverse collection of tasks to simulate in-context learning. This ensures the model learns to better activate the correspondence based on the given label data. Importantly, this activation is transferable across different tasks. So once training is completed, we can test the model frozen on a new task not seen during training. We find this training very effective, outperforming previous in-context learning and previous multitask learning. We also find this can be easily combined with a natural language description about the task, further improving performance. In fact, this recipe of combining in-context learning and task description remained to be the de facto recipe in 2024. This was adopted at scale, including Google's best model known to public, and Tulu version 2, the current state-of-the-art open ChatGPT-like model. Our work has been adopted to other settings, such as the multi-model, the pre-training setup, and the multi-model setup. Let me summarize what I've discussed. We discussed current language models, whose one of the most surprising capabilities is to do in-context learning. But we found in-context learning is more about learning the task format instead of input-output correspondence, unlike previously thought. And we could train the model to better activate its correspondence, which remained to be the de facto recipe in 2024. All of this indicate that the primary source of language models' capabilities come from language models' training data. This is very interesting because we actually never keep the data. The data is discarded and implicitly embedded into model parameters. This raises the question, is storing the data into parameters the only way to use the data? Can we use the data in a different way? This leads to part 2, which exactly answers this question by introducing non-parametric language models. So non-parametric models keep the data and locate relevant pieces and reason about them to make a prediction. By design, this model can better capture the full distribution of the data. It can easily grow or be seamlessly updated by keeping the data store up to date. A research question here is how do we design such a model that interacts with a data store? This is a very challenging problem because the data store is very large. It has billions and trillions of words, and it is impossible to read all the text in the data store. Today, I'll talk about 2 different approaches to build non-parametric models. First, I'll talk about a 2-stage pipeline called retrieve, then predict, which I've been studying since 2019 and now has been adopted widely to end application. I'll then move on to the next generation of non-parametric model that merges these 2 stages into one by making a non-parametric prediction. And I'll talk about what new opportunities it can create. Let me get started from the 2-stage pipeline. When a data store is very large, an intuitive idea is to find a more manageable subset of text and read it only more carefully. So that's exactly what we will do. We will first use a retrieval system that identifies a few passages that are most relevant to the input. Here, a passage means a block of text, usually somewhere between 100 to 1,000 words. Second, we use a second stage model to read over them and make a prediction. This idea is not new and has been existing for a long time. My research has built on top of them and has been some of the first representative work that modernized this approach. This is across different parts of the pipeline, including how to develop the retrieval system that identify more useful passages, how to train the second stage model to make best use of these passages, how to plug them together, and how to do an end-to-end evaluation of the system. This was later better known as retrieval augmentation and has been adopted extensively to end applications by Google, Microsoft, OpenAI, and several startups. Let me zoom into the first stage retrieval problem. Given a set of passages in the data store, Z1 to Zn, and a text input X, Our goal is to identify a single passage that is most relevant to X. Here we assume it's a single passage, but this can easily generalize to K passages. A neural approach to solve this problem has been also known as a Siamese network. We need a neural encoder that maps a passage into a vector. So offline, we map every passage in a data store into a vector space like this. And at test time, we map that input to the same encoder, project it to the vector space, and identify the nearest vector so that we can return the corresponding passage as an output. Nearest neighbor search over billions of vectors is not an easy problem, but fortunately, there has been research done here for decades, which makes it possible to do this search efficiently. Nonetheless, in 2019, neural retrieval was not the de facto method because there was no good recipe in training the encoder. It either required too much computation or labeled data. And even then, the result was not really better than alternatives such as lexical matching. Our work, called DPR, proposed a learning objective that is more effective, turning neural retrieval to be the de facto method. Here's the training recipe. Given the input X and a positive C+, which means a passage that is most relevant to X, we train the encoder using a contrastive learning objective that maximizes the similarity to the positive C+, against all the other passages in the data store, C1 to the end. However, computing this term over the entire data store is intractable. Therefore, we use a trick called in-batch approximation that approximates this term using other passages within the same batch only. And then, for these terms that refer to passages that are not a positive, which we call negatives, we make sure that they include hard negatives, meaning passages that the model is likely to mistakenly think as positive. This is very important because it challenges the model and makes sure the model learns how to avoid these negatives. So by combining these two techniques, we were able to train a competitive neural encoder.
This sounds similar to what people talk about as contrastive learning division. Are there any differences?
It's exactly the contrastive learning objective, but there can be many forms of contrastive learning objectives. For this particular problem, before DPR, people used the form of contrastive learning objectives that do not have negative. But one of the findings we have is having negative, especially hard negative, is as important as having a good positive. Around that time, there has been interesting debate going on parametric versus non-parametric models. For instance, Adam and Cohen thought, wait, parametric only is enough, or even better, as long as you have massive parameters. I was curious, so we gathered together, and with many others, hosted a NeurIPS 2020 competition to find out which approach is better. Here, a participant can explore either parametric or non-parametric approaches to better answer user questions. It was also one of the first to evaluate the time shift aspect of the model, so the model can be trained on data until a certain point, and we tested it on questions hosted 6 months later. This is the previous non-parametric model before DPR, and parametric-only model with 11 billion parameters. Parametric-only model outperforms the previous non-parametric model, which was very impressive to me. Nonetheless, DPR outperforms both models, surpassing the parametric-only model that is over 40 times bigger, and the gap is larger when there is a temporal shift. After the competition, it turns out that all top 8 submissions are non-parametric, all based on DPR, and the top 1 submission achieved a 42% relative improvement, which was very exciting. DPR had a significant impact on the community. Industry labs took DPR and scaled it up, both in the size of the encoder and the training data, and also made it completely unsupervised. Researchers made it multilingual and multi-model. Now DPR is a de facto retrieval model in the community, with numerous tutorials on the web and covering classes. So far, I've mainly discussed the retrieve stage of retrieve then predict. Once we have passages, we can give it to the second stage model and make a prediction. I'll keep it brief in the interest of time, but this is in fact another active line of research, and I'm happy to discuss more during the Q&A. Now there's a question. Yep.
You said that subsequently DPR was adapted to make it completely unsupervised. It sounded from your description like the distinction between positive and negatively labeled examples was key. So how did they move to
Yeah, so the question is about how exactly can we make it unsupervised? So DPR needed annotation for a positive, but not for hard negative. Hard negative can be done without annotation. But then, yes, it still is positive, which is still expensive to annotate. So in order to make it unsupervised, you need to come up with some ideas. And what some of the papers I put it here did is either two ways. One is to get some sort of annotated data from web data. For instance, you can use some question answering community like Quora, which is sort of a pair of question and positive. That's one way. The second way is you can generate a synthetic data where you take a passage and then you remove one sentence from it and consider the sentence as a query and the rest of the passage as a positive. So there are a few different ways to make the synthetic data for this. Other questions? Yeah, I can continue. So we all thought retrieve and predict is great, and that's the end of the story. But it turns out that this two-stage pipeline had several fundamental limitations. One of them is that each model component is trained completely in isolation, and end-to-end training of them is extremely difficult. Moreover, since this is a two-stage pipeline, there is inherently an error propagation issue. My research aims to develop the next generation of non-parametric models that address this issue by simplifying a two-stage pipeline into a one-step process. We designed such a model that makes a non-parametric prediction. Let me walk you through an example. Consider this input where our goal is to fill in the blank. An existing model does so by outputting a categorical distribution over a fixed output set of words. In contrast, what we want to do is to consider every contextualized word in a data store, words surrounded by a context. So there are billions of such words in the data store, and we want a neural model to assign a probability score to every contextualized word. So this often means a word to fill in the blank is green according to this context. Now, this model is very different from existing models that have a fixed output space. Instead, this model's output space is flexible and essentially infinite based on the data store. This opens up a range of new opportunities. For instance, now we can predict a phrase instead of a word by assigning a score to every contextualized phrase in the data store. We can also predict very rare or unseen phrases. For instance, imagine the model has never seen a word cadavra during training, then current models cannot predict this word. In contrast, our model can read the surrounding context and assign a high score even when the word is unseen. Let me formally define the inference process. Given a set of phrases in a data store, y1 to yn, and a test into x, our goal is to output a probability distribution over y1 to ym. We essentially need a neural encoder that maps every phrase in a data store into a vector space, and also the test input to the same vector space. So it looks similar to DPR, except now we are mapping a phrase instead of a passage. And then we can transform into the probability distribution based on which phrases are closer to or farther away from the input. I'll not go over training of this model in the interest of time. A short summary is we can take lessons from DPR in using a contrastive learning objective and in-batch approximation. But there's also new problems, so we came up with a few techniques to deal with that. And I'm happy to discuss more offline. Let me move on to the result. This graph, x-axis is the size of the model, and y-axis is accuracy. These are results of parametric only model with varying sizes. So the larger the model is, the better you get. If you add retrieve then predict, it consistently makes the result better. Finally, NPM, our model, achieves performance that is better than or closer to existing models despite having significantly fewer parameters. In particular, we found the gains are larger when it comes to long-tail entities, meaning rare entities, and when there is a temporal shift and we can replace the data store. There are a few caveats. For instance, NPM cannot be used for text generation as it is, but it shows strong promise in non-parametric prediction models. We'll continue some of the qualitative comparison between different models in part 3, so please stay tuned. Let me summarize what I've discussed on non-parametric language models. We started from a two-stage pipeline that first retrieve a set of passages and feed into the model to get the prediction. We then move on to the next generation of it that assigns a score to every contextualized phrase in the data store. Training these models poses unique technical challenges because dealing with a large-scale data store is challenging. Nonetheless, we were able to come up with techniques to deal with this issue. Our experiments show these models can better capture the full distribution of the data with fewer parameters and can be easily updated. So these are all great, but are we making use of all benefits of non-parametric models? One functionality we did not discuss too much is that we are using the data in two different ways. For training, and there's a data store, that means we could choose to put some data into one of them, but not to the other. Can we use this functionality to address an issue of current models? That led to part 3, where we discuss how to make these models more responsible. In particular, I'll tell you that training on all web data can be problematic, and a non-parametric model can offer a solution. So what exactly is the problem? The current practice is to collect all web text data as large as possible and train the model on everything. This can be problematic because a machine learning model can generate text that is substantially similar to the training data or even identical to the training data. So when the training data include copyrighted or private text, it could regenerate the data. Consequently, it is very natural for data creators to want to opt out from the model to prevent reproduction, or to get credited every time the model uses their data. This leads to legal risks to companies that develop and host AI models. They can get lawsuits for copyright infringement or for violating DMCA. This is literally a billion-dollar question. Nonetheless, there has been no good solution to tackle this issue. Companies typically retrain the model every time they have to remove the data, which is extremely expensive. Prior work explored filtering out any risky data and train on permissive data only for a specific domain like code and science. However, for most domains where there is no permissive data available, it is likely impractical. Given this background, here is our proposal. We propose to separate permissive and risky data, either public and private data, or permissively licensed and copyrighted data. And then we use a non-parametric model where parameters are learned on permissive data only, and the rest of the data is used as a data store queried only at test time. This model has truly unique properties. First, we can trace attribution back to the data for every model prediction together with any metadata like a copyright notice. Second, whenever the data owners want to opt out from the model, we can remove their data from the data store at any time with no additional training. These two features address many problems we discussed earlier on. Now we can give credit back to data creators, we can support opt-out, and we can mitigate legal risk by strengthening fair use defense or providing copyright management information. In the rest of the talk, I will showcase a case study focusing on copyright. Our model, called Silo, is in fact one of the first to mitigate copyright risk in a general domain language model. We'll focus on two quick questions. First, what challenges would arise if you simply filter out all copyrighted materials? And second, can Silo allows us to match performance of existing model trained on all web data? We've started from collecting a permissively licensed text corpus, since there is no such corpus out there. We call it OLC. OLC consists of 100 billion words, which is actually larger than previously thought. However, it turns out that the bigger problem is that its domain distribution is extremely skewed. Most texts come from government documents or permissively licensed code, which are very specific domains. There's very little other domain data like books and use, which are some of the most common data sources in other training corpus. This means models trained on OLC are likely to struggle with extreme domain shift. Once we have data, we train models on it and use the rest of the data as a data store and test. We compare two approaches we discussed in part 2, retrieve and predict, and non-parametric prediction. For evaluation, we focus on language modeling perplexity, so the lower, the better. We report parametric only silo, our model that is not using a data store. As a reference, we compare it with Pythia, an existing model trained mostly on non-permissive text. When domains are in distribution to OLC, parametric only silo is competitive. However, when domains are out of distribution, parametric only silo falls short. Next, we added a data store using retrieve and predict. It consistently reduces the perplexity, which is great, but it's still worse than Pythia. Finally, we added a data store using non-parametric prediction. It further reduces the perplexity, reducing the gap to Pythia by 90% on average. Let me take a look at a qualitative example. Consider this input, Voldemort cried Avada. If you have read a Harry Potter book, you know that the answer is Kadabra. But remember, our model has never seen Harry Potter books. It has never seen the word Kadabra. And therefore, this model cannot assign a non-zero score to an unseen word. This is true even with retrieve and predict. Even though we can retrieve the correct passage from the data store, the second stage language model cannot predict this word. Because again, there is no way the model assigns a non-zero score to an unseen word. In contrast, a non-parametric prediction model assigns a score not to a word itself, but to a contextualized word. So it can read the surrounding context and assign a high score to an unseen word. This is just one example, but when it comes to an extreme domain shift, like in Silo, it is not uncommon to encounter very rare or unseen phrases at test time. And that's why a non-parametric prediction model works overall better. Speaking of surrounding context, remember this naturally gives attribution back to the data together with copyright notice. And this is a key reason this can mitigate risk in copyright data use.
Maybe a smart detail, but you mentioned that you can now sort of predict vaccine words. Yes. I'm wondering sort of what happens with the input. So I guess don't you have tokenizers, and I guess tokenizers know this word, or is this sort of marked as like an unknown word or something during training?
Oh, yeah. So it probably depends on the details of the tokenizer. It can split it into like something like characters, or it could put it to the unknown word. Although even in the second case, when it's marked as unknown, you can still trace what the original word was, so you can copy that when you need to use it. Okay. So, I'll recap what I've discussed today and move on to the future directions and take more questions. So in today's talk, I discussed 3 topics where the central theme is rethinking data use. I first discussed rethinking how current models are using the data. In particular, I claim that current models use label data to teach the task format rather than the input-output correspondence. And we can train the model to better activate this correspondence. Next, we discussed rethinking how future models should use the data. In In particular, we discussed non-parametric language models that keep the data and use the data at test time. We discussed how to build such models, with experiments showing these models can better capture the full distribution of the data and can be easily updated. Finally, we discussed rethinking which data the model should use in what way. In particular, I claim that training on OLED data can be problematic, and a non-parametric model can offer a solution by separating permissive and copyrighted data and using them differently. All of this has been toward my long-term goal of research in building a next-generation foundation model of language that is scalable, accurate, and responsible. Certainly, we are not there yet. So what are the biggest remaining challenges? I must talk about the cost. I mentioned earlier that training current language models costs more than $100 million. But tomorrow's language models are even more expensive. Meta announced they will have GPUs that are equivalent to $24 billion. But why is it so expensive? It's because language models' capabilities turn out to correlate very well with the number of parameters and the training data set. And scaling each requires massive GPU computation. But in non-parametric model, there is a third factor, which is the size of the data store. That means we can scale the model with CPUs and storage, which are significantly cheaper than GPUs. Our preliminary work shows some promise. These are graphs from one of my work that show a clear improvement as the data store grows. Nonetheless, there are many fundamental questions left. For instance, what's the right architecture for better scaling? And how can we scale up nearest neighbor search to deal with trillions of vectors, beyond billions of vectors? These are the questions that we really should figure out. Aside from the cost, factual inaccuracy is an urgent problem. It's already affecting our life by spreading disinformation or affecting people's health. This is an area non-parametric models are critical, as factual knowledge represents a long-tail distribution of the data. However, even these models will make errors. No machine learning model can give you a 100% guarantee. Therefore, it is equally important to study interface for users to verify the model output and the source of information from the data store. Another underexplored area is how to answer harder open-ended questions, such as questions with false presuppositions. These are prevalent. For instance, more than 25% of Reddit questions include false presuppositions. Answering such questions require new modeling and evaluation, which I'm very excited to push forward. Finally, I should mention that the issues related to data use are continuously and significantly growing. Legal actions are continuously being made across different types of data like news, code, images, art, and music. More importantly, legal actions are simply indications of a more fundamental problem that the incentive system is completely broken. I think the fundamental problem is that the AI model is extremely centralized. There is this giant model that someone built, and that's it. No one else has control. But can we make it more decentralized? Can we have a non-parametric model where a data store is hosted by each data creator and be controlled by them? Beyond that, can parts of model parameters be owned by and controlled by individuals? And can we even make it work for other modalities like images, where copyright and privacy issues are just as, if not more critical than in the text domain? These are not just hypothetical scenarios as long as we have the right technical solution. And my goal for the next few years will be to come up with these technical solutions to make it possible. That is it. I'd like to thank my collaborators and happy to take questions.